All right, hello. Welcome back to another MathCons meeting. Today we're continuing 2011 Nationals, and we are on number 4 on team. So 6 standard dice are stacked on the floor as shown. On each die, the sum of opposite faces is 7. What is the maximum possible sum of the numbers on the 21 visible faces? So, we have 6 dice that are stacked like this. So it wants us to find what is the maximum possible sum of the numbers on the 21 visible faces. So if you count all the faces of these cubes here um that are on the outside and are not touching the ground, you will count 21. So then you can figure out it's just talking about the outward facing faces. So um So yeah, we want to find the maximum sum of that, and it tells us that on each die, the opposite faces always sum to 7. So if you think about this 3D, right? Um, so on one side of this cube stack, the 2D thing it just looks like this, right? Or pretend these are actual squares, right? But on the other side, it looks exactly like this as well, right? But flipped. But on the other side, each of these faces is gonna be with its opposite side, right? So and it tells us that the die's opposite side always sum to 7. So then there's nothing we can do about that. It's always gonna sum to 7, right? So each of these pairs of faces, one here, and then you have one here, one back there. So these 6 pairs of opposite faces like that, they're always going to sum to 7, right? So just from that, we can get that these 12 opposite faces together, they always have to sum to 42. And now we just have to find what is the sum of these two faces, these two faces, these two faces, and then the 3 faces that are going down here. Okay, so how are you going to do that? Well, we should look to see if there are any more opposite faces, right? Because that will just tell us it's a constant 7, right? Um, Now it might be difficult to spot a little bit, but there's actually an opposite face right here, right? So this face that's right here, and the top face on the vertical 3 face stack, right? So this and that are actually opposite faces, right? So that would also give you a constant 7. So then with that, that would bring our constant total up to 49. Okay, so then we're just looking for all those faces mentioned before, but we're excluding these 2 faces, which are opposite faces, okay? So let's look at these 2 faces first, and they're on the same die, right? Now, we want them to be big as possible. Well, we can't have them as both 6s, obviously, right? Because, a die can't have 2 6 faces, but it can have a 6 and a 5 face, right? And we can in fact put a 6 and a 5 here, right? Because it just wants the opposite faces to sum to 7. If we put a 6 and a 5 here, then we can just have its opposite faces being 1 and 2, and that's totally fine, right? And then the other opposite face it has here that we counted before in our constant 7, that's also still fine, right? Because if we have it as 6 and 5, we could still have this opposite face pair to be 3 and 4, right? And it still sums to 7, and then everything works out, right? So then the 2 faces on this die right here, we can have it as 6 and 5, right? And that would be the maximum value we can give it, right? So then we're going to want to add 11 to this for those 2 faces. And then these 2 faces on this die right here are also the same as this one. So we're also going to add another 11. Okay, and then the top die, we said 4 of these faces all around sum to 7, and then we just have one more face to consider. Well, if we just have this one more face to consider, and we want it to be maximum, we want it to have maximum value, then we're just going to put 6 on it, right? And that's not going to affect any of the 7 constant stuff because we can just have it as the other pairs, right? So 5 and 2 and 3 and 4, so that's fine. So we're going to add a 6 for that face. And then these 2 vertical faces right here, on the back of the dice, we can also just have those as sixes, right? Because you know, we could still have the opposite pairs being other stuff, and that's totally fine. So we're gonna have two more sixes, and then we just sum all this together. So 49 and 11 is gonna be 60, and then we have what, 18 and 11. So then it's 60 and 29. So then we have 89 maximum possible sum. And we can see that is our answer. Okay. Number 5. How many 3-digit integers are divisible by their digit in the ones place? Okay, so so really the best way to do this would definitely be like casework. So like I'm first gonna consider like 3-digit integers with a digit of 1 in their ones place, and then 3-digit integers with a digit of 2 in their ones place. So you know, why do we have to do casework and we don't do it some algebraic way? Well, I mean, if you think of doing this in an algebraic way, it would be pretty weird, right? Like you just generally I don't know, you just uh I don't know, this is just a better thing to do by casework. I don't know, algebraic would be kind of weird. Okay. So let's just do casework. Um so we can do so let's just start with 1, right? So case that the digit is 1. So let's just go through all 9 cases, and we will add all of their all of the ways that we can have that stuff together. So case that the digit is 1, well, we want the 3-digit integer to always be divisible by 1. Well, it's always just going to be divisible by 1, right? So then we just look for how many ways we can have the hundreds and the tens digits, how many ways we can have those and still have it being a 3-digit number, and you know, the ones place still has to be a digit of 1. So how many ways can we do that? Well, the tens place can be anything from 1 through 9, right? And or sorry, the hundreds place can be anything 1 through 9. If it's 0, then it's not a 3-digit integer. And then the tens place can be anything from 0 through 9, and you know, they don't affect each other, so we just multiply it by the number of ways, which is 9, and the number of ways on this one, which is 10, and then that just gives us 90 ways to do this. So case 1, we have 90 ways to do it. Okay, and then case 2, well, for something to be divisible by 2, it just has to be even, but because it's already 2 here, it's already going to be even. So then we're also looking for how many ways we can have like tens and hundreds digits, which is the same thing we were looking at case 1. So this is also going to be 90. Okay. Case 3, so we have a 3 here. So for something to be divisible by 3, the sum of its digits has to be 0 mod 3. 3 is already 0 mod 3, so that's just saying that these two digits have to be 0 mod 3. And so we can think of, well, there's another way to do this that might be a little bit faster. So it's just, you can just think of actually you can actually just think of each of these like 2-digit numbers being divisible by each of these numbers. So like, so let's say I had a digit D, right? If I have a digit D, and then I have I don't know, I have something here. Um as long as this 2-digit number is divisible by D, the whole thing is going to be divisible by D, right? Because this is already divisible by D, so like if you just think of it in long division, everything would work out if and only if this 2-digit number were divisible by D as well, right? So then actually for every case of this, you can just think of you know, how many 2-digit integers are divisible by our digit D. But you still have to do casework pretty much. There isn't like a great like formula representation of like I don't know, the number of two-digit numbers that are divisible by some digit d. But I don't know, doing the casework is still fine. It's not gonna take very long, or it shouldn't. And we do have calculators anyway on team if we need them. Okay. But so then for case 3, we just need to look for how many two-digit numbers are divisible by 3, right? And then so how can we do that? Well, if we think of the lowest two-digit number we can have that is divisible by 3, that would be 12, which is 4 times 3. And then the highest two-digit number that we can have divisible by 3 is 99, which is 33 times 3. So then, you can think that we have all of the middle multiples of 3 in here, right? So we're going to have 5 times 3, 6 times 3, ... all the way to 33 times 3, right? So then it's like we can count this based on what is being multiplied by the 3, right? And so then we can see that it's just going to be the range of 4 to 33 inclusive, right? And then so how many numbers are in that range? Well, it's just going to be 33 minus 4 plus a 1 because it's inclusive, right? So then that's going to equal 30. So we're going to have 30 numbers that are divisible by 32 digit numbers that are divisible by 3. So that will be the number of our case 3 numbers. And then case 4, we just need to look at how many two-digit numbers are divisible by 4. We can just do the same thing. So 12 is going to be 3 times 4. And then 96 is going to be 24 times 4. So then this would be 24 minus 3 plus 1, which would be 22. Okay, and then 5. So 10 is going to be 2 times 5, and then 95 is going to be 19 times 5. So then we're going to have 19 minus 2 plus 1, so then that's 18. Okay, and then 6, we're going to have 12, which is 2 times 6, and then we're going to go to 96, which is 16 times 6. And then this is going to be a range of 15. And then 7 is going to be 14, which is 2 times 7, all the way to all the way to 98, which is 14 times 7. So then this is going to be 13. And then case 8, we're going to have 16, which is 2 times 8, all the way to 96, which is 12 times 8. And then this is going to be 11. And then 9, finally, so we're going to have 18, which is 2 times 9, and then 99, which is 11 times 9. So then this is just going to be 10. Okay, and then we just need to add all these numbers together. Wait a minute. Wait, Bill, I did this wrong, didn't I? See, like for two, you don't just look at two-digit numbers that are divisible by 2, because then it would be 45. Yeah, see, it's actually not always gonna be like that. No, yeah, that was my bad. So like if you think of case 2, right? For something to be divisible by 2, it just has to be even, and because it already has a 2 in the one's digit place, it's always going to be even. So no matter what we have as the two-digit number, it's always going to be divisible, right? So it's not necessarily always going to be that the two-digit number has to, and it can only be a divisor of whatever digit we have. So we actually do have to look at this like more case by case. Yeah, that was my bad. Okay, but so for case 3, it should stay the same because so again, for something to be divisible by 3, the sum of this digit has to be 0 mod 3. So 3 is already 0 mod 3, so we just have to have the two-digit number numbers sum to 0 mod 3, right? Well, these two numbers sum to 0 mod 3. That's also just saying that the two-digit number has to be divisible by 3. So this is going to give us the same thing, which is what? Oh, I wrote it down, 30. Okay. But for 4, but for 4, it's going to be different. So 4, you always have a 4 in the ones digit. And then, so for 4, the only constraint is going to be that the tens digit has to be an even number, right? So if you recall, anything is divisible by 4 as long as its last two digits are divisible by 4, right? So we won't care about the hundreds digit at all in this. We will just care about the last two numbers being divisible by 4. And so how to do that is just to have the second digit always even, right? So if I have odd numbers, so like 1 or like 3, this will make this two-digit number not divisible by 4. But if I have any even number like 4 or I don't know 6, then this will always be divisible by 4. So then it just wants this tens digit to be an even digit, and then the hundreds digit has no constraint. So then it's not going to be this. It's going to be 100 digit has 9 choices, and then the tens digit just needs to be an even number. So that's going to be 5 choices. So then that's going to be 9 times 5 or 45. Oops. Okay. Okay, so case 6. So something ends in 6. So if we need this to be divisible by 6, it has to be divisible by 2 and it has to be divisible by 3. Well, it's already for sure going to be divisible by 2 because the last digit is even. We just need to have it divisible by 3. Well, the last digit is already 0 mod 3, so we just need these two digits to be 0 mod 3. Well, this was exactly like our case 3 case, right? So then we're just also going to want the two-digit number here to always be 0 mod 3, which just means that it has to be divisible by 3. And we already calculated that number up here, and it was just 30. So you can have 30 again. Boxes. Okay. Case 7. So 7, 7, you always need that the two-digit number will need to be divisible by 7. But how do you explain that, Bill? Bill. Is Bill? Are you there, Bill? I cannot hear you. It says you're muted on my screen.
Okay, what about now?
Okay, I can hear you now.
Okay, it was a system thing apparently.
So like for case 7, the two-digit number of like hundreds digit and tens digit always has to be like divisible by 7, right?
Right, yes.
But how would you like explain that?
Well,
Or how would you like, yeah.
so I mean, think about if you take the first two digits, if you look at them as a two-digit number, say like 7 times 3, that's 21, right? If you add a 0 to, if you multiply that number by 0, not 0, by 10, that's just adding a 0 at the end. So if you change that 0 to a 7, you're basically multiplying it by 10 and then adding a 7. So multiplying a multiple of 7 by 10, that still makes it a multiple of 7. And if you add another 7, that keeps it a multiple of 7. And yeah. yeah.
Okay, yeah, I guess it's just 7 is relatively prime to 10. And also that reminds me, I think I forgot case 5 in here actually. Yeah, I did forget case 5. Oops.
5 is pretty
Okay.
simple though. 5 is just any number.
Well, yeah. Well, yeah, 5 will just be any number because it already ends in 5. So, so yeah, this is just gonna be 90 again here. Um, but yeah, like Bill said, basically like I don't know. So like we can say so we have a 7 here, and then let's say the 2-digit number here is just called x. So then like the actual value of this number would be 10 times x plus 7, right? So for this number to be divisible by 7, we look at this in mod 7 and it has to be congruent to 0, right? Well, the 7 is already congruent to, there's already 0 mod 7, right? So basically we take that out of the equation, and then we just have, whoops, and then we just have 10 times x is congruent to 0 mod 7. Well, because 10 is relatively prime to 7 here, because it doesn't have any like factors or like it doesn't have um any factors of 7 inside of it, then like x has to contribute like all of the 7, I guess. Well, 7 is prime, but like I don't know, you should be able to see here that because the 10 doesn't contain the prime of 7, then x has to contain the prime of 7, which just means that x has to be divisible by 7, right? So basically here, because the 10 and the 7 are relatively prime, then the x has to just be divisible by the whole thing. So we can also think of that like in our 3 case, 3 was also relatively prime to 10. So that's also why we just had the 2-digit number having to be just divisible by 3. And yeah, so but like on the actual test, I don't know, you don't have to think like this deeply through. You can just remember like, if I have a 3-digit number and it needs to be divisible by 7, then like I don't know, like if the unit digit is already divisible by 7, then I need the upper 2 digits to also be divisible by 7. Okay, so then it's just going to be what we had before, which was 13. Okay, in the case 8, so we can also think about it like this. I do like thinking about it like this. So we can think about this like, let's just say we had x as our 2-digit number here again, and then we have 8. So then our number is 10x plus 8, and we need that to be congruent to 0 mod 8. Well, we already know the 8 is 0 mod 8, so we can just cancel that out. So then we just have 10x has to be congruent to 0 mod 8. Well, 10 contributes a factor of 2, right? So for the whole thing to be congruent to 0 mod, or for the whole thing to, for the whole thing to be congruent to 0 mod 8, where 8 is 2 cubed, then x has to contribute always at least a factor of 2 squared, right? Or more. And what does that mean? If something contributes a factor of 2 squared always or more, that just means it has to always be divisible by 4, right? So then for case 8, it's just saying that the 2-digit number in front has to be divisible by 4. And then how many of those do you need? You can just calculate it, but we already found it here, but we scratched it out. But yeah, it was 22. Okay. And then for 9, 9 is relatively prime to 10. So then it's just going to be the 2-digit number has to be divisible by 9, which is just going to be what we had before, which is just going to be 10. And you can also think of it as like the stuff before, where like, if we already have a 9 here, for something to be divisible by 9, this sum of digits has to be 0 mod 9. but we have 9, which is just just 0 mod 9. So then it's just saying that some of these two digits has to be 0 mod 9, which is saying that these two digits as a two-digit number has to be divisible by 9. But yeah, so for case 9, it just has to be the two-digit number in front has to be divisible by 9, and we just calculated that before as 10. Okay. So now we can just sum everything together. So it should be, we have 10, 22, 13, 30, 90, 45, 22, 30, and then a 90 and a last 90. Oh crap, wait, no, I did include case 5. Okay, wait. I think I might have, okay, so this is the actual case 5. So that was our wrong method before. So let me just head this again. So we have two 90s, we have a 30, we have a 45, and then we have a 90, and then we have a 30. Okay, and then we have 13, and then we have a 22, and then we have a 10. Okay, and then if you sum that all together, we get 420. And if I click, yeah, that is our answer. So yeah, you have to be careful on that. I don't know, like, what I was thinking was kind of right. Like, if you have the first two digits as divisible by the digit, then it will be divisible by the digit. But there are other numbers where the two-digit number in front doesn't have to be divisible by the digit, but the whole three-digit number can still be divisible by the digit. So it was just better to think of it either just, thinking of it in its like divisibility rules, which is fine, and you can go through that pretty fast. Or you can also just think of its mods, which are just like, more reliable, and you can I guess always think of like how and why it works. Okay. Anything else you want to say on that, Bill?
Um, hmm.
Wait, is
Uh,
my screen like frozen for you guys?
Let me check. Uh, what do you mean frozen?
Uh, do you only see like, or
Nothing is
look at
moving
my
right now, by the
timer?
way. Nothing is moving right now, so.
No, yeah, look at my timer in the top right.
Oh,
Does it
right.
say 8:02?
Yeah, 8:02, 10 seconds, yeah. Oh, it is frozen.
Uh, how has it been frozen? Okay, looks like it's working
Yeah,
now.
it's working.
Sorry about that, I guess. Anything else you want to say on this problem?
Um, it's kind of long, I guess. Not really.
There wouldn't really be any other way to do it other than casework, would there?
I guess not. Probably not. Just thinking about it. Yeah, this probably isn't because this isn't. You can't really generalize something like this. So it has to be casework.
Yeah, unless you did something really smart, but that would be,
We're not
I don't
smart
know,
enough to do that.
you're not smart enough.
Alright.
Okay. Next problem, number 6. Okay. Given that measure A is 60 degrees, BC is 12 units, BD is perpendicular to AC, C is perpendicular to AB, and the measure of DBC is 3 times the measure of ECB. The length of segment EC can be expressed in the form A times root B plus root C units, where B and C have no perfect square factors. What is the value of A plus B plus C? And I'm assuming that it wants our A, B, and C to be integers, even though it doesn't specify here. It should, but I'm assuming to be that because usually when they put something to expression like this and they have like variables into it, then the variables are gonna be integers, and you're not gonna have non-integers in like square roots. Like it doesn't want you to put it like that. Okay, but anyway, we're gonna assume it to be integers, but I should have specified in the problem. Okay. So we're given like some information about this triangle. We should just try to write out like all the information, right? Or like as much as we can, I guess. And then, write it all out and see if we can figure out anything. So it said that A was 60 degrees, and then BC was 12 units. BD is perpendicular to AC, so like right here. And then CE is perpendicular to AB, so like right here. And then measure of DBC, so this is 3 times the measure of ECB. So if we call ECB x, then DBC will be 3x. So you can look at this for a bit, maybe think a bit on your own. But one thing to notice here is that in this quadrilateral right here, we have 3 of its 4 angles. So that means we can just figure out its 4th angle just by simple geometry, right? So, this is at 90 degrees, this is 90 degrees. Quadrilateral internal angles has to add up to 360, so this angle has to be 120 degrees. And then from vertical angles, we can see that this angle had to also be 120 degrees. And then you can see we've gotten an angle into this triangle with some more of our variables and stuff, so that's helpful. And in this triangle right here, we can see that 120 degrees plus 3x plus x has to equal 180 degrees. So then 4x has to equal 60 degrees, or x has to equal 15 degrees. Okay, so cool. So from that, we found that, x has to equal 15 degrees. Okay. So, let's look back to the problem. What do we have to find? We have to find the length of segment EC, and yeah, we're expressing it in that radical form. So how would we find the length of EC when we have, these angles and we have this side? Well, if you look at ECB, it told us that EC was perpendicular to AB. So this right here is also going to be a right angle. So then you can see that ECB is a right triangle, and we want to figure out what EC is. We have what the hypotenuse BC is, and we have what this angle X is, right? So from that, you should be able to see that, we can do some trick here to relate all three of those variables. Well, we have 2 of those variables, so then it's really just making one equation with one unknown variable, and then we can solve for that and hopefully find our answer, right? So let's do that. So we need to set up a trig with our angle X here, and we needed to relate BC and EC. Well, BC is a hypotenuse, and EC is adjacent to X. So we could do cosine of X, and you can think of like SOHCAHTOA, this will have to equal the adjacent over the hypotenuse. So cosine of X will have to equal the adjacent to X, which is EC, over the hypotenuse, which is 12. And well, we know what x is, but we need to evaluate what actually the cosine of x is to find the radical form of EC. So you need to find cosine of 15 degrees. Now you shouldn't really have I don't know, cosine sine of like 15-degree increments memorized. Well, like if you do, that's fine. That's great. Then you can just go ahead and put that in. But normally most people just memorize like trig of angles just in 30-degree increments. In or 30-degree increments plus like 45 degrees. But that's fine. That's really all you have to all you really need to know, because you can just derive like cosine sine any trig of 15-degree increment angles by using just some basic trig like formulas and identities and stuff. So I will show you how to do that here. So we're gonna derive what cosine of 15 degrees is. So first we have to know a few identities. So, or I mean, really just one identity actually. So the identity we have to know is that cosine of an angle A plus an angle B will equal the cosine of angle A times the cosine of angle B minus the sine of angle A times the sine of angle B. So we just need to use we just need to use this for this because we just need to use this. But there's also a sine version that is useful to know, and it is applicable in other situations. So if you don't know the sine version, also you should also know this version, which is sine of A plus B is sine of A cosine of B plus sine of B times cosine of A. Okay, so we're not going to use the sine identity here, but it is useful to know, and if you do not know it, you should get to know it. So yeah, so if you have not already memorized these identities, I would say you should get to know them, and memorizing these are more important than saying like memorizing trig of like 15 degrees and stuff, because you can just derive it from these formulas. Okay, so now let's go ahead and derive cosine 15 degrees. So the trick here is we want to put 15 degrees into this format where 15 degrees is the sum of some two angles, and we need it so that the two angles that we have it as a sum of, we need these two angles to be like well evaluable in cosine and sine. So it'd be preferable if it was like nice angles, like 30, 60, 90, 45 or something like that. But you might be wondering, like, if we're adding two angles to become 15 degrees, won't it always have to be like something smaller than 15 degrees? So then it would be like, even harder to figure out what those are than actually 15 degrees. Well, actually, you can actually put one of these angles as a negative angle, right? And then you can put this in terms of nice angles, but there's going to be one angle that's going to be negative, but that's still fine, because you can still like find cosine and sine of like easy angles but are negative, but I mean that's still pretty easy. So what we're gonna do here is we can say cosine of 15 degrees is equal to cosine of 45 degrees plus the negative of 30 degrees. So then, this is like having our A equaling 45 degrees and our B equaling negative 30 degrees. Right, so this is helpful because then we can put it into this format and then we can find, cosine and sine of 45 degrees and negative 30 degrees relatively easily. Um, you can also put this as cosine of 60 degrees plus negative 45 degrees, as this also sums to 15 degrees. And it will also give you the same answer. So you can test both of them out. But really, it doesn't matter which one you use, so you can just go with whichever one. But so let's just use 45 degrees and negative 30 degrees. So we just need to evaluate what this is to find what cosine 15 degrees is. So from our identity above, this will equal cosine of 45 degrees times cosine of negative 30 degrees minus the sine of 45 degrees times the sine of negative 30 degrees. Okay, so let's just evaluate this now. We should be able to evaluate this pretty easily since these are all nice angles. So cosine 45 degrees is just going to be root 2 over 2. And, if you don't have your, like these nice angles, the trig of nice angles memorized, you probably should. Well, I mean, you don't necessarily have to have them like memorized. Like, I guess you can always like derive them, but I mean, make sure you can do it like pretty fast or like kind of know it off the top of your head. Because I don't know, for like nicer angles like 30, 60, 90, and 45 and stuff, in math competitions, you're generally needed to more know that stuff like just off the top of your head. Um, so like I don't know, like in math count sprint, there might be a lot of like, or in countdown or whatever, there might be a lot of cosine and sine of these nice angles. And you're supposed to know them already, like without using a calculator or anything, without using any calculation really. So yeah, so if you don't already know like these off the top of your head, you should get used to them, I guess. But I guess it'll also kind of come naturally as you work in math. But yeah. Okay, so cosine of 45 degrees is root 2 over 2. Cosine of 30 degrees is going to be root 3 root 3 over 2. Well, but okay, so sorry. Cosine of 30 degrees normally would be root 3 over 2. But we need to think about if the negative 30 degrees will change anything. Well, if you think about the unit circle, do I have any space? Okay. So you think about the unit circle, if we map some angle theta, and on the unit circle where this radius is 1, then we can model the cosine of this angle theta as the x-coordinate of where this line intersects with the unit circle, right? So this would be cosine of theta. So we could also think about this with some negative theta, right? So we put this on the other side, we have negative theta. Then we can see this will intersect with the unit circle here, but it will be symmetric over the x-axis. And you can see here that, it will give us the same value of cosine theta. So it will actually give us, so cosine of a negative angle will actually give us the same value as the cosine of the regular angle. Or like, you can always negate the angle in the cosine of whatever, and you can just evaluate that and it'll always equal the same thing. You can also see this on the other side, if I had some way larger theta, or let me just draw a new unit circle. Okay, that's actually a pretty nice circle. Okay, so if I had like an obtuse theta, this actually still works because, our negative theta would be like this. So our cosine theta would be like right here, and it is negative, but our negative theta here would also give like the same cosine theta here, and it is also on the negative x-axis. So it works for all theta. So cosine of whatever angle, the angle inside is not affected by any negatives. We can always negate it and whatever, but it will not change the value for cosine, right? So you can say cosine of negative 30 degrees is equal to cosine of 30 degrees. And then cosine of 30 degrees is root 3 over 2. Sine of 45 degrees is root 2 over 2. Now, what is sine of negative 30? Well, sine is actually affected by negative angles, contrary to cosine theta not being affected by negative angles. So you can see here, if we look at this model, this right here, the y value of this intersection would be sine of theta. And then the y value of this intersection would also be, well, it would be sine of negative theta. But you can see that the sine of negative theta, this is on the negative y-axis rather than the positive y-axis here. And, because you can see that it's symmetrical about or over the x-axis, then you can see that the magnitude of sine of theta and sine of negative theta are the same, but just that they are on opposite sides, right? So then I just think here that sine of theta and sine of negative theta are going to be opposite signs. And we can also look at this diagram with obtuse angles just to make sure. Sine of theta right here, it's going to be that. And sine of negative theta right here, it's going to be this. And we can see again that, they're on different sides of the y-axis. So they are going to be the negatives of each other. So yeah, so cosine, you can always negate the inside and it will be the same value. But for sine, if you negate the inside, then you also have to negate the outside. So sine of negative 30 degrees then would equal the negative of sine of 30 degrees. And we know what the sine of 30 degrees is. It's just going to be 1/2. So then we're going to put an extra negative in there. And then this is our whole expression. So then we have root 6 over 2 plus with that negative, root 2 over 2. Or sorry, oh my bad. The bottom should be 4 actually. Okay, and then we have plus root 2 over 4. And then, I don't know, just putting the top together, then we have root 6 plus root 2 over 4. Okay, so this was our cosine of 15 degrees. So now we found that cosine of x is equal to root 6 plus root 2 over 4. And this was equal to EC over 12. And, we wanted to find what EC is. So we just need to multiply by 12 on both sides. So then we're going to have 3 times root 6 plus root 2. And then you can see we have it in this format that they wanted us to have. And these are all integers, and the radicals don't have any perfect square factors. So then we just want to know what's the sum of all of these numbers. So then we just want to find what's 3 plus 6 plus 2, which is just going to be 11. And you can see, yeah, that is your answer, 11. So is there anything you want to say about that, Bo?
Crit, yay. I don't really know what to say about this, so. Yeah.
Okay.
This is mainly your problem.
It's just chasing angles and some trick. Yeah. Okay. Let's move on to number 7. Do you want to take over now, Bill, or do you want me to start before then?
Let's see. You want to do it after this problem because I think you are the one who mostly did this problem anyways.
Okay, that's fine. Okay, we have number 7. How many ordered pairs of positive integers x, y satisfy least common multiple of x, y is equal to 400? Okay, so what what does the least common multiple function do? Well, um, so um, let's say we have least common multiple of x, y, right? Um, I feel like yeah, I think we talked about this multiple times in the past, but I will just quickly say it again. So if we have x and y, and we prime factorize it, so we're gonna have like 2 to the power of, let's just say um I let's just say a1, 2 to the power a1, 3 to the power a2, um 5 to the power of a3, and so on. And then y is like 2 to the power of b1, 3 to the power of or sorry, b2, 5 to the power of b3, and so on. Then what the least common multiple is doing is, for every one of these primes, it's looking just for which one of these is bigger. So is A1 or is B1 bigger? So and whichever one is bigger, it's gonna take that one, and the new number, the number that is given by this function, um, it will have two in its prime factorization. It will have two to whatever number is bigger here. So if B1 was bigger, then the LCM factorization would have B1 here. But it doesn't mean that it always has to take, Y's factorization for all of its numbers, because because like or like we look at it separately for all the primes. So if A2 was larger than B2, then we would do 3 to the A2. So it's not always just the exact prime factorization of one number. Then it would just be like either of these numbers, right? Um, maybe that's a little bit weird, but you can see it much easier if you just like look in an example. So I don't know. Let's just do LCM of something random. Okay, so let's just do 84 and um, 482. That's pretty random. Okay, so we want to look at the prime factorization of these numbers first. So 84, I could take out a 4 from that. So 2 squared, and it's going to be 2 and 1. So that's 21. So then we have 7 and 3. So you have 2 squared, 3 and 7 for 84. And then what is 482? Well, we could take out a 2. So then we have a 2, 4, 1. And then 2, 4, 1. Is that prime actually? Uh, hmm.
241. I can check.
Here, I don't know. Let me just use a let me use something
It is prime.
cooler as an example.
It is prime, by the way.
Okay, no, I'm gonna use something cooler as an example. Okay, I'm gonna use 98. Okay, so prime factorization of 98, we can see that we can take out a 2, and then we will be left with 49. And 49 is just 7 squared. Okay, so then the prime factorization of 98 is 2 and 7 squared. Okay, okay, so then how do we get the LCM of this? Well, for each of the primes, we want to find what which one has the largest like exponent of that prime, and we're just going to take that exponent and we're going to put it on our new number. So we're first going to look at the 2. Well, 84 has 2 squared, where 98 only has 2. So that means we're going to have 2 squared in our LCM. And now we look at 3. Well, 84 has 1 3, and 98, it's like there's a non-existent 3 here, right? It's like there's a 3 to the 0 here, right? But this is a 3 to the 1. And so, 3 to the 1 is bigger than 3 to the 0. So we're just going to take 3 to the 1. Okay, and then 7 and 7 squared. Well, 7 squared is bigger than 7, so we're going to take 7 squared. So that's going to be our new LCM. Okay, so it's just like that. Pretty simple. Um, I guess I don't know. Um, like I want I want to um I don't know. I'll talk about this later with you, Bill, but whatever. Okay. So okay, back to the problem. So okay, we need it so that so we're looking for LCM of x and y equals 400. X and y are integers, obviously. We're just looking for their pairs. Okay. So as you can see with like our LCM stuff, uh, something very important was like prime factorizations. So you want to know what the prime factorization of 400 is. Well, um, I don't know. If you do it, it's just 2 to the 4 and 5 squared. I don't know. You can see that easily because it's just 4 times 100. So 4 is just 2 squared, and then 100 is just 10 squared, which is just, or 10 is just 2 times 5, so then 10 squared is just going to be 2 squared times 5 squared times the original 4, which is 2 squared, then you have 2 to the 4 times 5 squared. Okay, and so the LCM of x and y is equal to 2 to the 4 and 5 squared. Now, if you remember about the LCM stuff that we just talked about, um, each of these prime factors of our LCM result, each of these was like a copy of either one of these numbers, right? Um, so like the 2 to the 4, it has to be, fully either from x or y. Like um, either x has to have 2 to the 4 or y has to have 2 to the 4. Basically like um, one of them needs to have 2 to the 4, right? So like I don't know. Let's think about you know what if well like you can just think of it as like if as we saw before, like each of these was taken as a copy from one of these numbers from the prime factorization of one of our original two numbers, right? 2 squared was taken directly from here. 3 to the first was taken directly from here. 7 squared was taken directly from here. It's always taken directly from one of the numbers. So 2 to the 4 and 5 squared, they both had to be taken directly from either x or y. So then that's saying either x or y has to have 2 to the 4, maybe both, but it can't be that neither of them have exactly 2 to the 4. And also same thing with 5 squared. Okay, so then let's just think of um so like 2 to the 4 can either go to x or it can go to y. 5 squared can either go to x or it can go to y. So maybe one thing we can think of this is that um we have we have we have initially four ways to arrange where our 2 to the 4 and where our 5 squared goes. Okay, and then so so let's just say our 2 to the 4 and 5 squared both end up in x. So then what can y be? Well, because 2 to the 4 and 5 squared were already taken from x, then y can be y's 2 and 5 factors. They can be anything as long as it's smaller than or equal to 4 and 2, right? Because if y had a larger factor of 2 than what x has, where x already has the factor of 2 to the 4, well then the the LCM function of this will copy y's 2 instead, and y's 2 would not be 2 to the 4, right? If y's 2 was 2 to the 6, then LCM would copy 2 to the 6, and then LCM would have a 2 to the 6, but we see that 400 does not have 2 to the 6, right? So y's 2 has to have, equal to or less than 4 here. Okay, so then that means the exponent of 2 here has to be somewhere between 0 and 4. So that's like 5 choices. And same thing for 5. You can use the exact same reasoning for 5. So we can go between 0 and 2, sorry. And that's 3 choices. And this, y can't have any other factors, right? If y had, 1 factor of 3 or any more than just 1 factor of 3, then 400 would have at least 1 factor of 3, right? Because then it would take this 1 factor of 3 over x is no factor of 3. So then 400 would have those extra factors, but we only see 400 having factors of 2 and 5, which means that y can't have any other factors. It's just going to have this, right? So that means, in this case, we can see that y would have 15 combinations, right? And it seems like for every case, wherever you put 2 to the 4 and 5 squared in, it's always pretty much going to be like this, right? Let's say the 2 to the 4 went to the x, and the 5 squared went to the y. Well then, same thing as before, except these are separated into the 2 different numbers, but that doesn't really matter, because here again, we have just the same reasoning with the same 2 to the 4, right? It has to be either smaller, this exponent of 2 has to be either smaller or equal to 4, right? Because if it was greater, then it would take the greater one, but it is only 4. So then it has to be less than or equal to 4. So then it looks like another 5 here, and by the same reasoning, it looks like another 3 here, right? So in all of these cases, it looks like they're going to be 15 cases, and it looks like we're going to have 4 cases in total, right? That's just the number of ways to arrange where these two big factors can go. So then that would just give us 4 times 15, which would give us 60 cases or pairs, right? But we do have to be a little bit careful here. We have to be careful of not to overcount any cases. And I don't know, if you think about this a bit, you will see that we actually have overcounted some cases. So, let's just think of the case where x and y both have 2 to the 4 and 5 squared. So both x and y are like this. Well, when we count it like this, how many times do we count this? Well, one time we counted it where 2 to the 4 and 5 squared were both on the x. Another time we counted it where they were both on the y. Another time we counted it where 5 squared was on the x, 2 to the 4 was on the y. Another time we counted it where the 2 to the 4 was on the x and 5 squared was on the y. So we can see that we counted this case 4 times, right? But we only want to count each case 1 time, right? So then we would have to subtract 3 from our total number of pairs, right? Just from this case alone. So now we have to think of any other cases that we could have possibly overcounted. Well, let's think of the cases where we have both of the numbers having 2 to the 4, and then let's just say x has 5 squared for now, and then y has some factor 5. Well, we're looking at a different case here from this case. We don't want it to be the same case because from this case we already subtracted its overcounts. So we don't want this to be a 5 squared, but it still needs to be, less than 5 squared, right? Because if it was more than, then the LCM would have more than 5 squared, but it only has 5 squared. So then, this has to be either 5 to the first or 5 to the 0. Basically, you can choose from the range of 0 to 1. So then there are 2 cases here. So then, so just from this case, you can see that we've overcounted this, okay, so I don't know, you can think of this as like, sorry, You can think of this as like two separate cases. So we have 2 to the 4 5 squared and 2 to the 4 5 to the first. And then we have 2 to the 4 5 squared and 2 to the 4 5 to the 0. Okay. So let's look at this case first. This case is overcounted by where we look at where we put the 2 to the 4 and the 5 squared at. So we could have put the 2 to the 4 and the 5 squared here, or we could have put the 2 to the 4 and the 5 squared here. So those we counted, those are two possible cases we could have counted it, and we've counted it both times like that, right? So we've overcounted this case one time. And then same thing with this. I know it's the exact same thing. So we also overcounted this one time. So then we need to subtract two of those overcounts. But you can also see that we could flip this 5 squared over here, right? We can have the x instead have the 5 to the first and the 5 to the 0, with the y having 5 squared. And then these are different cases. We've overcounted them differently. So we will need to subtract these overcounts as well. So we'll need to subtract those two overcounts. So like you can see that the overcounting happens when both of the numbers have like both of either 5 squared or 2 to the 4 or both. So we already looked at the case where both of them have 2 to the 4s. So now we have to look at the case where both of them have 5 squared. So let's say both have 5 squared, and then let's say x has 2 to the 4. Well, the y's 2, we can't have it as 2 to the 4 because then, we're overcounting the cases. We're trying to count the overcounted cases of this one again, but we don't want to overcount the overcounts, right? If we overcount the overcounts, then that's also going to be bad. We're going to be subtracting too much. So we don't want it to be the same case. So we don't want it to be 4, but we need it to be less than or equal to 4. So then it has to be 2 cubed or lower. So then, this can be 0 through 3, right? And no matter what this exponent is, we're always going to have the overcount of where we're putting the 2 to the 4 and the 5 squared, right? If we're putting it here, that's one case. If we're putting it here, that's another case. So we're always overcounting this by 1. And again, we can choose this, or we have 4 separate cases here, right? So then we're overcounting all of those by 1. So then we're overcounting this whole expression by 4. And then, but you have to remember that we can also flip this, right? We could also have the 0 through 3 on the x and a 5 squared here, and the 2 to the 4 is on the y, and still 5 squared here. And this would be the exact same thing as, well, not like the exact same thing, but it would give us the exact same overcounts. But they are not overcounts of the overcounts, so we still need to subtract this from our original number. So then we had to subtract both these 4s, so we had to subtract an 8. Now, there aren't any more overcounts because the overcounts resulted from, the possibility of, in these cases, we could have the 2 to the 4 and the 5 squared being put in different cases. So then, like, both the numbers had to have either like both of 5 squared or both of 2 to the 4. But we've already looked at all of that. So then that's just going to be it. So then we're going to have 60 minus all of this. So that's going to be 60 minus 15. And then that's going to give us our final answer, which is 45 pairs. And then you can see that is your answer. So yeah, you have to be very careful about overcounts on that. You also have to be careful of overcounting your overcounts. Yeah. Anything you want to say about that one, Bill?
Yeah. So yeah, when you're counting, just you're counting, you gotta be mindful of how many times you're counting each thing, basically. Okay. Do you want me to take over now?
Yeah, sure.
Okay.
Um, although we only have like 7 minutes left.
Oh, that's true.
Maybe you can get this probably.
Okay. Okay. So we're gonna look at problem 8. So a subset of the integers 1, 2, 3, dot dot dot. My bad. 1 to 3, dot dot dot. 400. Oh my goodness. There you go. 499, 500 has the property that none of its members is 5 times another. What is the maximum number of members in such a subset? So it's saying that none of its members are 5 times another. So for a number to be 5 times another, that number has to be 0 mod 5, right? So first of all, you can include every single number that's not 0 mod 5. So that's just that will be 100 times 4. That's 400 numbers. Those are all the numbers that are not 0 mod 5. So now let's think about the numbers that are 0 mod 5, right? Because that's not, because if you think about it, let's see, something like 25 will work because we aren't including 5 because 5 is 5 times 1. But 25 works because since we're not including 5, we can safely include 25. So 25 works. And if you think about it, so let's think about the next one. So we first thought about 5, right? Because we can't have 5. But we also can't have 10 because 10 is 2 times 5. If we can't have 10, then we can have 50. So if we look at this, it's basically just every multiple of 25, 100, but we can't have 125 because 125 is a multiple of is 5 times 25. In 25, we are including 25. So if you think about it, if we're only looking for the maximum number of members in a subset, so if we were to include 25, we can't have 125. If we were to include 125, we can't have 25. So it doesn't matter which one we include, the number stays the same in the end anyways. So we can just go ahead and just include 25 for ease of counting. So from this we can see that basically it's just every multiple of 25 that's not a multiple of 125. So that just ends up being 25, 50, 75, 100, and then 150, 175, 200, 225, not 250, 275, 300, 325, 350, 400, 425, oh, 425, 450, and not 500. So this is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's just 15 numbers. So it is 400 plus 15. 415 numbers.
You forgot 475, I think.
400. Oh, my bad. 475. So that should be 416 then. Oops. Yep, 416 numbers. Okay. So next problem. In triangle ABC, point D is on segment AC with AD to DC equals 2 to 1, and point E is on segment AB with AE to EB 2 to 3. Segments EC and DB intersect at point K. What is DK to KB? Express your answer as a common fraction. So something to note about this problem is that it says that there is a triangle ABC, but if you look at the way they're constructing every point in the triangle, there's actually no limitation on how this triangle can be constructed, right? It only specifies the point where the points are, but as for the triangle itself, there are no limitations for it. So what this means is that you can use a triangle that's beneficial in this case. So we've thought of two ways to do this. So one way is that we can have a angle. We can have, let's say, I'm just gonna draw it here. You can have A, B, C like this and like this. This is E, D. So if we draw like this, that's bad. Okay, if we draw like this, then this is 2, this is 1, this is 2, this is 3. Yep. We draw like this. Because we can manipulate the triangle however we wanted to, what we can do is that we can make the triangle so that the line CE bisects the angle ACB. Because that way we can use the angle bisector theorem on triangle CAB and triangle CDB. And we can use that to get a ratio. So we can see if we were to make the triangle so that CE bisects ACB, then the ratio of AC to CB will be 2 to 3. So since AC is 3, CB will be 9 halves. And now, because we've previously established that CE bisects ACB, we can also use the angle bisector theorem on CDB. So, and the ratio would be 1 to 9 halves. And we're looking at the ratio of dk to kb. So dk is 1, kb is 9 halves. So that gives us the answer 2/9. And that's your answer. Another way we thought to do this was because you could make the triangle whatever you wanted, you could make the triangle a right triangle, and um, so a good like Pythagorean triple that we thought of that's like easy to solve with would be the triple 5, 12, 13, because that way you can have both of the sides that are being split up as legs, and therefore they're like perpendicular to each other, and that makes it easier to work with. So we have A, B, C. So we can have this as the 5 side, this is the 12 side. So we have D, E, and this will be 8, 4, 2, 3. We can connect these. And yeah, this is K. So at this point, when I was doing this, I actually just coordinate bashed it at this point because this is fairly easy because these are all fairly nice points. Like if you were to coordinate bash this, you basically are just going to have y equals negative 6x plus 12 and y equals negative 8 over 5x plus 8. And like these aren't that bad of equations, and it wasn't super complicated because you were given the y-intercept here. So this isn't that bad to coordinate bash. Um, Me and Austin also discussed the possibility of trying to
Okay,
prove.
well, wait, can I say something?
Yeah.
So for this problem, like the main thing to notice is that like think about like what you can do, like you like what you can do with the problem that still satisfies the constraints but like makes the problem easier to work with. So I don't know, like kind of doing like without loss of generality stuff, but like you're making it like easier. So like if you just try to solve this raw, you might see that it's like very hard. Like if you labeled all of the sides as like variables and stuff, you can see that, you know, like there's like a lot of variables and not like I don't know, like equations that you make will kind of be messy and you can't really find any nice ones. So I would say like the thing to notice is that you can make like the sides like basically um like the main triangle sides ABC, you can make that like um anything you want, and the ratios you can still have the ratios be the same, right? So so like Bill said, like one way you can do it was you can have that 5, 12, 13 right triangle, and that's kind of nice because um you can have those um like the ratios separated as integers, and when you're also like messing with the sides of the triangle, you can also see that you can get like one of the angles Bill was talking about to be an angle bisector. But yeah, so I feel like that is like the crux of this problem. Um, unless they were intending for you to solve it raw, but I feel like that would be way too hard.
Yeah, solving it through generalizing will be very difficult. Me and Austin were trying to do it, and we were kind of struggling. That's what we were doing before we started this. But
Yeah.
yeah,
Um,
something take a takeaway from this is just that when you have like a geometry problem like this, pay attention to what the problem allows you to do with like your thing, and like just try to like m- use that to your favor. Like, don't make stuff harder than it has to. If it lets you make it something easy, then like just make it something easy.
yeah. Okay. So it's 9:04. Um, so that's gonna be it for this math counts meeting. Well, we were one problem off of finishing. Okay. But yeah, so we will finish this last team problem from 21 Nationals next week. And you guys can let us know whether you guys want us to do like 2010 Nationals or like some earlier Nationals like 2019 or 2020 or 2018 or something like that. Or we could also do like countdown or like math counts trainer if you guys wanted to. I think last meeting Lee Sean said that he wanted to do 2010 Nationals. So
Yeah.
you know if Lee Sean still wants to do that, then we could just do that. Okay, but that'll be it for this meeting. So thank you for coming and goodbye.